Okay, so welcome to my part of the Advanced Cosmology course. My name is Sten Hannestad, and I've done this in other courses too. I plan on primarily, for now at least, doing lectures in this way. So I record them using a normal Blackboard and in some cases PowerPoint. Then each 2-hour block of lectures will typically consist of approximately 60 minutes of this type of recorded lecture, plus then a 30-minute discussion session, which we'll do online via Zoom. And I hope this is an acceptable format, but otherwise we will figure it out as we go along. So for my part of the course, we will be using this book. It's called Modern Cosmology. It's by Scott Dodelson. It's a standard textbook in the field. So it's mainly related, if you want, to theoretical cosmology, and that's indeed primarily the part that I will cover. So let's just very briefly look at some of the topics that we will go through. So the first thing is, since not everyone in the audience presumably has had a course in general relativity, then what I want to start out with is just if you want, a crash course on general relativity. Of course, it will not really be a course in general relativity. We'll just take some of the most essential elements which we will need for the cosmology, and then basically leave everything else. I will not do many derivations because it's too cumbersome and it takes too long, and we won't be able to do real cosmology. But at least we need some introduction to general relativity. And then the next part, once we've established this, is to do what is known as standard Friedmann-Robertson-Walker cosmology. So that's basically taking what we've established from general relativity, so that's the field equation, the Einstein equation as it's known, and then the equation of motion for particles, what we call the geodesic equation. Once we have those, then we're essentially good to go. Then we can look at standard Friedmann-Robertson-Walker cosmology. So that's basically the normal homogeneous and isotropic cosmology, where the cosmological principle applies. Everything looks the same in all places. The universe expands. That can be described in relatively simple terms using this formalism. And once we are through that, then all the interesting stuff happens, if you want. So then we can start to talk about what we could call freeze-out processes, which is really just deviations from thermal equilibrium in the universe. So at least for the time being here, we will remain in the approximation that the cosmological principle applies, namely the universe is homogeneous and isotropic, but we will look at particles, meaning photons and dark matter and baryons and so on, which can be in thermal equilibrium with each other or with other particles, or out of equilibrium. So this is completely needed, an understanding of this phenomenon, to understand, for example, the cosmic microwave background. How is it formed? Why does it look the way it does? We need it in order to understand the formation of light nuclei in the early universe, what is known as Big Bang nucleosynthesis. That's another essential part. We also need it to understand how dark matter can be produced, how dark matter falls out of thermal equilibrium in the early universe, and plenty of other things that we may or may not have time to cover. Okay, so once we're through that, then we need to relax the next assumption, namely homogeneity and isotropy. And that brings us to what will take up a very substantial part of my lectures, maybe even most of them, and that is what we call structure formation. So we will start out in linear perturbation theory. We'll start out with small deviations from homogeneity and isotropy. once we have a theory working for these small perturbations, then we can use those, for example, to look at the cosmic microwave background radiation. We can use them to look at galaxy formation and such things. Then we proceed, after we've established this, then we proceed to nonlinear structure formation. So that's essentially large deviations from homogeneity and isotropy. So that's of course anything to do with galaxies or clusters of galaxies in the present day universe where they have much higher density than the surrounding medium. And that can be treated using a variety of numerical methods. Then we'll look at some observations of cosmic structure formation. So that's, for example, gravitational lensing, etc. And then the very final part of my lectures, if we have time for it, which I think we will this year, will be devoted to the very early universe, so what we call inflation in the early universe. So what essentially is it that generates the initial conditions for the hot Big Bang that we see in our current universe? So how do you set the initial conditions? How do you make the universe geometrically flat? How do you make small perturbations that since then grow into galaxies and clusters of galaxies and so on? That's not really exactly known, but we have a working theory for it, which is observationally confirmed up to a certain limit, and that we will discuss. I will also, if I have time, discuss, for example, what is known as baryogenesis, so the formation of more matter than antimatter in the early universe. That's also something that we'll look into if time permits.